Hello everyone, welcome to this webinar hosted by Rockflow Dynamics. Thank you for logging in to join us today. It's Joanne here from RFD's Aberdeen office. Today I am hosting this session with my colleague Mike, who is our presenter, and we also have Maria, who will be helping us with the Q&A. Today we are bringing you the first instalment of our three-part new energy series. So at Rockflow Dynamics, we have found that more frequently our users are asking us about how they can use tNavigator for projects related to new energy. So we devised this program to give you an overview of the features and workflows within our technology. After watching our webinar, if you have any further questions, please do not hesitate to reach out to our team. We can share more information. We have lots of tutorials and some examples of how clients have been using tNavigator to facilitate their energy transition initiatives. So Mike's presentation today is going to focus on solutions for geothermal energy. Mike will demonstrate how our parallel software architecture and integrated workflows between Reservoir Geomechanics and surface network modelling allow you to use tNavigator to efficiently and effectively model geothermal processes. Due to a large number of attendees, everyone has been automatically muted. Excuse me. So if you would like to ask a question, please type it into the chat box, and we will answer as many as we can at the end. If we don't manage to address your question live, we will make sure we follow up with you on email as well. We will also be recording the session, so that will be uploaded to our YouTube channel later on today. So now I am happy to hand over to Mike to begin the presentation, and we'll be back at the end for the questions. Thanks, Mike.
Thank you very much, Joanne. Good morning, ladies and gentlemen, or wherever you are in the world listening to this. As Joanne mentioned, we are going to start with explaining exactly what geothermal energy actually is before going through the integrated processes that tNavigator can offer. So what is it? It actually starts with the name geo and thermal. So geo meaning heat, thermal meaning, geo meaning heat, geo meaning earth, thermal meaning heat, of course. In short, it's a renewable resource that uses natural heat flows from the subsurface to heat fluid, mostly water or isobutane, which is then produced and used to generate electricity or heat. So some brief applications for this are maybe to heat homes, schools, factories, things like that. To heat waters for fish to thrive in fish farms, maybe fish that aren't resident to the climate that we currently have. To heat greenhouses to grow food, again, not particularly suited to the ambient climate around. To heat milk for pasteurization. This is actually quite a big application for geothermal energy, which is not really thought about a huge amount. And of course, to generate electricity. These are some of the big ones, but of course, there are many other applications for geothermal energy. Now, the reason we started this new energy solutions series is because, as Joanne mentioned, we've seen a massive uptick in requests to us around the subjects of CCS and geothermal. So let's see how this correlates with the global reality. On the image on the left, we see the top 10 geothermal energy producing countries in 2021. The vast majority of these utilize petrothermal methods. These petrothermal methods essentially are the hot rock method, whereas the hydrothermal methods are mainly due to geothermal gradients linked with the subsurface or shallower aquifers. So if we see the USA is obviously by far the largest, and then we have things like Indonesia, Philippines going down to the top 10 at the bottom there. I think US, certainly when I looked at it, was a bit of a surprise, but then I looked a little bit more into it, and you see actually most of the areas are around the San Andreas Fault and of course Hawaii. Indonesia, Philippines around, they're obviously part of the Pacific Ring of Fire. Another example, Kenya, the East African Rift is around Kenya. So these are all the petrothermal, geothermal methods mainly. The top right image shows geothermal power generation and capacity by region. Unsurprisingly, Asia Pacific and the US produce the most energy. Again, Pacific Ring of Fire, and the US just has by country has a large amount. Europe is in third place. However, they have a slightly mixed capacity or methods for getting geothermal energy out. The production methods are fairly split. So Italy and Iceland, for example, utilizing petrothermal. Etna, Vesuvius for Italy. We have obviously Iceland, self-explanatory, I think. However, countries like Sweden, Germany, France are quite large hydrothermal energy producers, and ever growing as well over time. And we can see this obviously with the general uptick of that graph. Year on year, so 2017, year on year, we can see that there is more energy generated by geothermal methods to where we are now, 2022. I think this goes up to 2021, and then the last two bars are predictive, I guess, but ever increasing. Finally, the bottom right image indicates the number of geothermal wells that have been drilled globally over the last 32 years, which is overlaid by CapEx, which is the line essentially. So this shows a gradually increasing trend by the kind of start of the 2010s. The graph also towards the right-hand side starts to predict what expects to be drilled over the next sort of 8 to 10 years, which you can see shows a dramatic increase. So now when we get to 2021, as I said, everything's referenced to 2021, we see that the current planned wells are in pink. So that even still you can see is at least flat. And then in grey, you can see that that line massively uptakes, and that's what they expected, things that haven't been actually planned yet, but are potentially expected to be planned. So in summary, the demand for geothermal projects has increased massively, has increased over the last 10 years and is predicted to continue rising at a much faster rate going forward. Now, most common geothermal systems in Europe will probably be hydrothermal. It's more efficient, and in Europe we do not have that sort of too much of the hot rock petrothermal side. These work generally by drilling new wells or working over existing wells that be from flooded hydrocarbon reservoirs or potentially aquifers as well. Production wells produce hot water from the subsurface through a geothermal gradient, which then either flows through a form of heat exchange, such as a building of some sort, as I said, school, factory, things like that, or goes through a turbine to generate electricity, especially if steam is produced. The water, if it is steam, is then condensed, circulates through the system, and is injected back into the subsurface for pressure support. Now, something quite interesting with this as well is that when you see the lifetime of a project, you will generally see the time, the breakthrough time from injector to producer, because you'll see a temperature difference between the two, as the injected water is colder than the produced water naturally from the aquifer. Geothermal project life cycle. We've kind of split it down into three main domains, certainly applicable to tNavigator. These start with exploration side, the feasibility side, and then the development and monitoring side. Now, as I said, we're going to keep it in our terms mainly, but just as a brief overview of all three, we'll start with the exploration side. Now, data is gathered, such as seismic data, old logs in pre-existing wells, things like that, especially if they're being worked over. And then a static model is built to test any hypotheses that you have at that particular stage, the exploration stage. Old seismic data can be reinterpreted if needed in areas more applicable to the geothermal area, especially if you're using things like old reservoirs. And then prospective well locations are then discussed at this point. On the feasibility side, initial resources and volumes are then derived from the static model, potentially also multiple static scenarios that have been built to obtain a range of volumes. This is kind of the advised workflow, and certainly a workflow that we see is used more and more, very, very often actually. These are fed then into the dynamic modeling side, where hydrodynamic properties are added to test water flow through porous media, again testing these hypotheses at the feasibility side. Field development plans and well plans are created and added to these models, as well as surface network constraints, such as restrictions on capacity, and also building a general picture of what that closed loop system could be. Forecasts are then created, and hopefully integrated static and surface uncertainty can be performed to create multiple scenarios and evaluate overall economic feasibility. On the development and monitoring side, well, of course, this comes a lot from any kind of well testing that you have, and ultimately the hardware side, so gauges, topsides, subsurface, etc. Subsea, sorry. At this point, the project comes to life, and when it comes online, the models are constantly updated. The models are then calibrated to observed data. Using history matching, we can match to this observed data, and of course create new economic forecasts based on the calibration, the history match, and new hypotheses that we also have at this point. Now, how do we do this in tNavigator? We offer a fully integrated solution from reservoir modeling to which is fully implicitly linked to geomechanics, PVT with multi-component water. We can have various salt types into that, etc. Wellbore pressure and temperature loss modeling with temperature gradients and heat transfer coefficients, to fully implicit surface network modeling to illustrate this closed loop system that we have with the geothermal modeling side, and also predict surface losses at the same time. This is all encompassed by the link to what we call AHM and uncertainty, where we can add variables to any part of this system and run them through, say, an experimental design algorithm or an optimization algorithm with an objective function. This is ultimately to quantify uncertainty and mitigate economic risk. Now, on the slide here, you can see anywhere we have the magic wand, this is the ability to add variables into these areas, and you can see it's everywhere within this workflow that we have. Now we will go through each of these steps and milestones, and we'll see how these can be achieved within tNavigator itself. So we'll start with the static modeling side of things. We started with the data reconnaissance or data gathering, where seismic images, data from samples, logs, etc. can be loaded into the project. If seismic's been added, it can be tied to wells, depth converted, and further manipulated to allow surfaces to be interpreted, which will ultimately detail units in the geothermal reservoir, which can be then played with. The surfaces are then added to structural modeling processes to build a grid for facies and petrophysical properties to be defined using variograms, statistical algorithms like sequential Gaussian simulation, truncated, etc. Volumes can be calculated from this static model, and of course variables added to any part of this process to create ranges of your volumes or resources that you have available. As we mentioned previously, these then get fed into the dynamic building process, where we then apply hydrodynamic properties to them. A couple of examples in the top left-hand corner of this slide. So I'll just build two dynamic models here. One petrothermal, one hydrothermal. And you can see the kind of these are both temperature maps. You can see the hot rock aspect of the petrothermal side versus the geothermal gradients of the hydrothermal side there as well. Within the dynamic modeling part of tNavigator, of course, we attach it to our PVT. And we mentioned that we have black oil compositional and thermal aspects of tNavigator. We can use various salts, we can use multi-component water, as well as just a simple black oil and regular water parameters by correlation. Of course, then we build a development strategy within this as well, and you can add in things like your injected water temperature. Of course, plenty of additional information and parameters we can add in temperature related, be that from the black oil extended temperature option that we have, but also on the thermal side. Now, well placement optimizer is used essentially for multi-editing a series of wells if they are needed for the geothermal model. Now, of course, individual wells can be added using simple hotkeys. For those who've seen tNavigator before, the simple Alt-click to add in a well, very, very simple. But if multiple wells are required to be planned, we have this tool that allows you to add in these multiple wells in patterns that you define. Now, we have preemptive template patterns, but you can also build your own customized patterns there as well. This is just a quick 5-spot producer injector pattern that we see on the example. The well trajectories and structure for injectors and producers can be defined, as well as defining things like tiebacks to facilities, drilling schedules, and plenty more. Of course, as with any part of tNavigator, variables can be added to this area, namely for well trajectory optimization, where you can add them to your sort of well geometry, your XY coordinates of your well, completions, things like that. Now, geomechanics, extremely important to consider in geothermal models due to the injection production nature of the systems. Rock failure criteria through Moore-Coulomb or Barton-Bandis is available, as well as wellbore stress states, roof deformation and subsidence, and induced fracture direction due to overinjection. All these can be modeled within tNavigator in the same reservoir model. Also, we can model Young's modulus and Poisson's ratio, which is dependent on pressure and temperature as well. And we're constantly improving and adding to the geomechanics side of tNavigator. The real benefit with this is that it is fully implicit and coupled with the reservoir. So this means that all equations are calculated in the same system at the same time for each iterative time step. Of course, I know you're going to get bored of me saying this, but we can add variables into any part of tNavigator. Geomechanics is no different. And we can add variables to the actual geomechanical properties, the initial properties, and run them through uncertainty workflows coupled with other parts of the workflow, like static modeling, dynamics, and more as we go through the presentation. You'll see, ultimately, this actually is crucial on the geomechanics part because you are mitigating risk in a massive way in terms of wellbore integrity and reservoir integrity as well. Now, going up to the wells towards the surface, the integrated well modeling that we have allows you to load and edit well trajectories and structure, and also links with the same fluid project as the dynamic model and also the surface network, which we'll see in a second, with the ultimate aim to build our VFP curves, producers and injectors. Now, these curves can be matched to any observed data, well test data that we have, by applying variables to well structure, different correlation parameters, things like that. And these can also be added into wider uncertainty studies coupled with the reservoir and geomechanics. More specific to the geothermal modeling side, we have temperature gradients and heat transfer coefficients that we can add to this, which is this center image on the slide here, which model heat losses in the wellbore due to heat exchanges between the fluids and the reservoir. And of course, the wells then connect up with the surface network, which we now see on the next slide, which, like previous areas we've discussed, connects fully implicitly with the reservoir and the wells, and geomechanics was coupled with the reservoir anyway, and calculates all equations in the same system for each iterative time step, as well as having the ability to apply variables to, of course, to any object parameters that we have within the surface network. These can be run in a joint system of uncertainty workflows. The example we see here is a heat dispersion network with 2 producers, a pump, 2 injectors on the right-hand side, and a heat sink in the middle. This is just a very, very simple example. The heat sink has been defined as a pipe with just thermal conductivity and heat transfer coefficient on there as well. This ultimately just loses heat. However, it can be defined as a Python object if you have a certain specification that you have, and this object can be completely customized to whatever your needs are instead of actually using the pipe itself. Now, all of this we've talked about is completely pointless if we do not have interactive results analysis, and of course tNavigator does. It's one of the things we're very well known about. A few examples of we've added on here some dynamic grid properties, and you can see in 2D these are some just contours that we have, as well as a well section window. You can see this in cross section, graph vectors. We can see lots of different graph vectors, temperature based, pressure based. Of course, fully coupled with the surface network. So whenever you run the reservoir itself, the surface network also calculates at the same time, of course, with the geomechanics there as well. Now we're going to go on to a quick video next, just to show the reservoir side of things coupled with the geomechanics. So without further ado, let's have a look. Now, just on the left-hand side, we can see some of the initial properties we've defined, including the initial properties defined with the geomechanics. So Young's modulus, Poisson constant, any active blocks we have with geomechanics there. Now, the just added on to as a calculator, a dynamic temperature profile, and now running the model, you can see how the temperature profile is changing through time. And we can, of course, visualize this in 3D cross-section and 2D cross-section, obviously. When you move the time slider, you can see exactly how the temperature is changing based on the injector that this cross-section is now covering, and also now the second injector is covering. So blue is obviously colder, and we're having colder water injected into a hotter system. Now we're going to create a quick profile. You can do this by cross-section as well. Profile is just a block center version of a cross-section. So building a profile, visualizing this now in 2D. So again, just using the drop-down menu to visualize the profile we have with the two injectors. And you can see one of the producers is also incorporated in this. It's just a part of the producer actually. And we can see how obviously the temperature is changing through time. Now, if you right-click on any grid cell, you can look at your block info. It's just an IJK block with some parameters at the bottom, or vectors we can see. So now we're just visualizing pressure, temperature, and actually water molar density as well, which is of course 100%. We have multiple graphs additionally we can visualize. So look, some of these are analytics graphs for inducers and producers. So now we're looking at bottom hole and tubing head temperatures. You can look at injection temperature, and of course on the right hand side you have all of the results available in table form. Now back to the geometry or grid properties, and in 3D just going to go through some of the geomechanics areas. So these are all dynamic now, they all change with time, so you can have a look at all the displacements, effective stresses for minimum, maximum, different vector directions, and of course you can click on each of these and see how they change with time if needed. We can also visualize these in cross section, and again we're just adding the same cross sections on we've used for the injectors, injector 1, injector 2, and again you click on any of the geomechanical maps we have and you can see how they change with depth, and due to the fault we do see some differences. We also added some traces, just simple water traces into this model, and you can see how the water is dissipating away from the injector. It was also based on the geology there as well. So you can see at the bottom left-hand corner of that tracer has been blocked by the geology, potentially a shale zone there. And in interblock flows, we also have some transmissibility models where we can see the exact transmissibility or thermal transmissibility in this particular case. Between each particular grid cell. And finally, now just before the video ends, we have a well section window. We can visualize temperature, and again changing everything through time. You can see at the bottom we can add geomechanical properties onto this as well. Just added it on for the injector and the producer, and of course if you move the time slider, everything changes through time. You can make these as simple or as complex as you would like. You know, we can also add on our grid scale, which adds in a scale of our IJK blocks next to our TVD subsea or measured depth if we wanted to visualize that as well. This is just a very, very simple overview of what we can do within tNavigator. We've mentioned uncertainty a number of times throughout this webinar, so I think it'd be only fair if we let it shine with its own section. Just a few points around how this applies to geothermal. The way we integrate uncertainty from various domains is using embedded workflows with the model designer as the master workflow. The workflow you see in the greenfield example on the right-hand side adds variables to the following parts. So you can see right at the top, items 1 to 5, we have added variables onto horizon depths. This incorporates basically the seismic uncertainty that we have. And from that, new grids are created. Obviously, when the horizons change, a new grid has to change, and new properties are then populated on top of that. So this is where you can see things like Fashi's modeling and property interpolation. Of course, you can add variables into those if you wanted to. It's just a very simple example. Item number 6, we have fault transmissibility used as a variable. There's a major fault throughout this model, and this will obviously change the fluid flow throughout that fault. Item number 7, we have linked it with the PVT designer, and this we've actually changed the molar fraction of our components within our multi-component water, and so therefore you're getting a different fluid also flowing through in your uncertainty study. The next items 8 to 11, we have 4 wells. Basically, those are the 4 items here, and we have just added variables onto the frictional wellbore. Onto the inside tubing, inside roughness of the tubing, which takes into account the frictional wellbore losses going up to surface, and therefore our curves, our VFP curves, will be changing each scenario. And finally, as well, the item number 12, we have just added a variable onto the thermal conductivity. This is to model the temperature drop over the heat sink. So you're dispersing different amounts of temperature over that particular pipe. Now, items 7 to 12 are embedded workflows, using the model designer as the master workflow to ultimately connect to our AHM and uncertainty domain of tNavigator. Now, why are these important? Like conventional hydrocarbon projects, geothermal projects rely on production forecasts to evaluate if the project is financially viable or not, as well as to understand the reservoir characteristics. Now, multiple scenarios mitigate this risk a lot more, which is where experimental design and optimization algorithms with objective functions come in. Development strategies are defined within forecasting, and the incremental is then calculated between each scenario in order to get your ultimately best case and plan to go forward with. Now, over time, excuse me, apologize. There we go. Now, over time, these models are updated with observed production and production injection data, temperature data. This is all calibrated. The model is then calibrated to this observed data, essentially, using history matching tools, as we just with the same algorithms that we just talked about previously. And these multiple history match models can actually be used to base your multiple forecasts on. If you don't have variables in your forecast, you can just use the history match multiple cases as a base. If you do have them, you can use forecast optimization, and again, using going back to the well placements editor, you can add variables onto your wellbore geometry, XY coordinates, production controls, injection controls, things like that. Now, economics optimization. Financial decisions for geothermal projects are very complex, in part due to the lack of established regulatory rules and challenging government incentives, which are ever changing. This twinned with a need for heavily front-loaded capex for feasibility studies, exploration, drilling, testing, makes multiple scenario modeling completely, crucial. It's really, really important to mitigate this economic risk through uncertainty. Now, tNavigator actually links with Microsoft Excel and basically to your economic spreadsheet. Now, each defined parameter in the spreadsheet is updated based on each scenario that's calculated by tNavigator automatically. It's just linked with a Python script, essentially, which we can, of course, help you with. The benefit cost ratio is then calculated and can be used as part of the objective function for forecast optimization. So you can actually optimize your forecast based on your economics spreadsheet and parameters that you deem are important, NPV, for example. Now, to conclude, tNavigator is this fully integrated solution, which obviously matches the closed loop solution that you have within geothermal models. And we can model this using black oil with our extended temperature option, but also using our compositional thermal engines as well. Now, reservoir, geomechanic, surface network models, well models can all be calculated fully implicitly in the same system of equations for each iterative time step. So they're all converging at the same time. There's no managers here, there, and everywhere. It's not two-way. It's all fully implicit. These embedded workflows allow you to quantify uncertainty through each individual step. Now, of course, you can break it down and do multiple uncertainty workflows for certain parts, or you can all add it into the same uncertainty workflow and quantify this uncertainty with all parts together. Now, this can obviously be done for history matching. It can also be done for production forecasts, and it can be done for economic forecasts as well. And as we mentioned previously, this would be kind of pointless if we didn't have a state-of-the-art graphical user interface, which is completely interactive, very time slider and time dependent, of course, and everything is linked together. If you run one area, the other area will calculate at the same time. Just to finish off there as well, we do have another geothermal reservoir simulation case study. This was done by a client of ours, I believe 3 or 4 years ago. So please check out our YouTube channel, RFD Europe YouTube channel, and you'll be able to see that webinar there. Thank you very much for listening. I'll pass over to Joanne.
Thank you, Mike. Yeah, so we can move on to some Q&A now. So Maria's going to help us. I think she's been reading through the questions that have been coming in. I'll quickly mention before we go on to the questions. So you can join us same time next week for the next instalment. So next week we're going to be moving on to the topic of CCS. So Alexei will be demonstrating our production engineering workflow for our CCS project, showing you how we can incorporate all the elements of the field into one project in tNavigator and carry out all your calculations fully implicitly. So please join us again next week. Maria, do you have some questions?
Yes, thank you so much to all for the questions. We actually got few questions. I'm gonna just read aloud few, and then the ones that we are not managed to answer will be responded by email. So the first one is it possible to give the characteristics of a fluid that can be used for transfer heat into the surface? You're muted, Mike.
It's only been 2.5 years, right? Geez, yeah. So it's in essence, yes. Your fluids are obviously dependent, temperature dependent. So viscosity of the fluid will change based on your temperature. The two types of fluids that we can essentially create are black oil fluids and done by correlation, and also thermal based, so compositional / thermal. So you can break them down into their individual components, and also have things like K values, which to the thermal side of things. So yes, obviously, of course, those fluids do transfer heat, and you are using that same PVT project for the reservoir, for the well model, and also for the surface network model. So you don't have to reproduce it in any way.
Okay, thank you. Another question is, within tNavigator, can we plot together the phase diagram of the injected fluid and then the pressure and temperature profiling within the wellbore?
Yep, absolutely. Now we'll start with the phase envelope there. Yep, you can plot that phase envelope. You can obviously visualize the bubble point, dew point, critical points on this, cricon and therm, cricon and bar, etc. That's all that can be visualized in the PVT part of tNavigator. And the second part was plotting pressure and temperature on the wellbore. Is that correct, Maria?
Yes, that's correct.
Yeah. Okay, so on the wellbore side, yes, you can plot. I think of this actually. Yes, I mean, obviously the wellbore is attached to the reservoir and also to the surface network, so you can plot the temperature and pressure profiles within the well section, like we did actually on the video briefly. And the initial part of the wellbore modeling, you can also define as a temperature gradient as well. So you have the static side, your input, and you also have the dynamic side about how the temperature and pressures are changing down the wellbore, which can be visualized in your reservoir.
Okay, do we have time for another one, John? Yeah. What output do you optimize to select the best development strategy in a geothermal case besides NPV?
Good point. Good question. Okay, NPV is obviously well, any economic parameters are obviously very important. The output as well. I think you need to make sure that you have your geomechanics and your wellbore integrity and your reservoir integrity is all up to scratch. So linking to the geomechanics is very, very important for that. Doing these integrated studies and making sure that you have these multiple scenarios, actually then going back to the economics, also allow you to model how close you are to your break-even point or within financially for the project. On the more sort of modeling side, I guess on the surface network, you need to make a best estimate of how much you are actually constrained by on the surface network. It's all well and good producing a load of hot water, but then if you can't actually handle that at the surface, there's no point. So you need to obviously create adequate surface network models. There are loads of different outputs that you really should look for, but of course tNavigator ticks a lot of these. Yeah, for sure.
Yeah. Can we model escape precipitation when water is being produced instead of steam?
Escape precipitation.
Scale.
Scale precipitation. Scaling. Oh, I think we can actually. I think so. Scaling, we can. Yeah, we've just added it fairly recently, I believe. So we can. Yeah, we can actually model scaling and hydrates. We can look at the hydrate curve. We're about to add in hydrates modeling into the wellbore modeling side of tNavigator very, very soon as well.
Okay. Another question is related to heavy oil. Can tNavigator run scenarios of hot water or cold water injection combined with a low salt or polymer injection?
Okay, this is one maybe we would probably get back to you in a bit more detail on, but in short, yes. I mean, we can run heavy oil projects. We can use SAGD. We have ASP. We have lots of different polymers that we can use within tNavigator to move heavy oil, for sure. But this is something that we'll have to get back to you in more detail about.
And I guess the last one for being the time would be why did you choose fully implicit to run the model?
Well, fully implicit.
Considering it's computational expensive.
It's computationally expensive, but I think if you look at the world these days, the computational side and the hardware side is improving drastically, including the use of GPU cards. And fully implicit modeling allows us to run the models actually faster. They're much more.
Oh, you got to mute.
Oh, sorry. Yeah, and you can build much more complex systems as well. So it's not only the fact that you can run them faster, they're more scalable, but you can also build more complicated systems. For us, we build everything from the same code from the ground up. There's no third parties. It's just a completely private development, if you like. So we know the code. We know we can do it. So why not? It's a better solution.
Okay, we have more questions, but actually quite few. But during the time, we can respond them by email. Thank you so much for everyone who asked questions and attended.
Thank you. Yeah, we'll gather up all those questions and get the detailed answers out to everyone individually. And we'll also make sure the recording's on YouTube later on today, so you can have a look at that as well. Cool. Okay, dokes. Well, we look forward to seeing everyone again next week. Thank you, Mike, for the presentation, and thanks, Maria, for your help as well. And thanks to everyone who joined. See you all next time.
Thanks, everyone.
Bye.
Thank you. Bye.